Now let's look at a number of functions that we've written over lists again using the standard design pattern. And given the discussions we've just had about accumulators or not, I've collected here only functions that are actually supposed to be written in this style. And let me actually use consistent alignment if I align the equals in the other definition. So we have the definition of elem, the definition of map, and I've also given a definition of and here. And is essentially a generalization of the binary logical AND operator to lists, where we check just as the binary AND operator essentially is only true if both arguments are true. What the list-based AND version amounts to is that it checks whether all elements in a list are true. And perhaps the only slightly, let's say, non-trivial case here is actually convincing yourself that AND of the empty list should be true, because all elements in the empty list are obviously true, and also because we want that if we recurse on the tail of the list and we ultimately hit the empty list, that of course we are not destroying our entire result. So we should have something here that is neutral with respect to the binary AND operator, that does not change the result, because if we would AND everything with false for the empty list, then the whole result would always be false, right? So AND of the empty list should be true, and then AND of x cons xs is just x and, like the binary and the the list-based AND function on x's. So this is also something, again, with the reasoning that we have this shortcut behavior for AND as much as we have it for OR, that should better be written using the standard design pattern and not an accumulator. All these functions are very similar to each other. They all, elem and map take some extra argument, but they ultimately all take a list, right? And these actually take general lists, and this takes a list of booleans, but that doesn't matter very much. And they all produce a result, and the result has different types, but they all take a list to some result. And they all have two cases, one for the empty list and one for the cons. And they all have a recursive call to the tail, right? Here the tail of the list is ys, and we call elem on ys. Here the tail of the list is xs, and we call map on xs. And here the tail of the list is xs, and we call end of xs. And in fact, in all these cases, the recursive call is the only way in which we use the tail of the list. We only use the tail of the list by making a recursive call. So this is all similar between these three functions. And it is actually what I've been describing as the standard design pattern on lists so far. Now, we are in a functional language. We can abstract from everything, and that is one of the strengths. So we can define new functions and have parameters that are themselves functions. So one of the consequences of having such a language is that whenever we see any repeating pattern, we can abstract from this pattern and define a new function that captures it. And that is something that we can do ourselves, and I'm going to demonstrate this here. And the way that we do this is essentially by just, first of all, we give a name to this function that we're going to write. And because we don't yet really know how it will turn out, I'm just going to call it fun for function, or because we are going to have some fun while we're going to discover what this is going to be about. And in this case, I'm not going to bother with the type signature, because I'm actually going to rely a little bit on the type inferencer to help me. And instead, but the idea, right? The idea is, nevertheless, is that we have something, perhaps taking some extra arguments, and then taking some list of A, and then getting some result out. So that is certainly what I'm going to expect to see from the type inferencer, as something of this shape, if I'm going to do things correctly, right? But what I'm going to capture is that, again, I'm expecting there to be possibly some extra arguments here, but I'm expecting to see that we are covering this pattern of having two cases. So I want to have a case for the empty list, and I want to have a case for the non-empty list. Okay. And now actually the type inferencer already gives me this shape that I wanted to see, list of A to P. Okay. Now, what else is possibly the same in all these three, apart from having these two cases? Is there something the same? Perhaps I can actually even make the naming a little bit more symmetric by, I don't know, this is perhaps not necessary, and I'm perhaps making my life harder this way, so that the list that I'm matching on in all three cases is always going to use the X cons XS pattern, which is reflected here, so that we are a little bit have an easier time matching up different pieces. Now the results here, in the empty list case we return false, in the map case we return the empty list, in the AND case we return true. There doesn't seem to be all that much similarity between the results in the empty list case. So that is perhaps something that we should just leave open. And the idea is that if we are doing this, abstracting from common patterns, there are always going to be things that are also different. Some things are going to be the same, and other things are going to be different. But for the things that are different, we're just going to make them parameters of our pattern. Like the function fun that we're just creating will get extra parameters, so that we can instantiate the function fun to different versions of these parameters later on, and then get the original functions back. So I'm going to call this result in the empty list case, I'm going to call this nil with a lowercase n, and that is just a name for the result, and we're going to make this a parameter of this function, and that means that our function here will get an extra parameter nil, which we'll just pick up. And now the type of the function changes, but essentially at the end, the inferred type here still has list of A to some result. Okay, so that is the important part. Now, what about the cons case? For the cons case, okay, that's also clearly different. For example, here we are using or, and here we're using cons, and here we're using and. So we clearly need another parameter. But there are certain aspects that are still the same, and namely that this operation that we're doing here is always operating on x, right? So it's doing something with x, which is only available in this case. So we should like somehow use it, and it's always making a recursive call to the function. Okay, so perhaps we give a placeholder name, let's call it cons, but we pass to this placeholder the things that we're supposed to use always. And the things that we're supposed to use, look, if I just made a placeholder cons and give this a name, right, then whatever I put here cannot actually use x and xs at all, right? Because x and xs are in scope here on the right hand side, but I'm now filling in cons, and cons comes from the outside, and it doesn't have access to anything of the list that we're currently analyzing. So that's not good enough. So whatever we're doing here is supposed to have access to x, but now the interesting thing is that we don't give it access to xs directly, but instead we are just giving it access to the recursive call of our function. And that matches the idea that we have here. We're going to give it recursive access to fun, and now I have to repeat the arguments cons and nil and xs. Now this looks like it is similar in style to the functions that we have seen above, because again, we have matched the 2K structure, one for the empty list, one for cons. the result in the empty list case is completely flexible. The result in the cons case is parameterized by a function that gets access to the first element of the list and the result of recursively calling the function. That is captured here. And now we've seen that the inferred type is actually has become quite a bit more spectacular. So let me actually click that in. It's using T1 and T2 now. So I think it is slightly clearer perhaps if we rename T1 to A again, because that is our element type of the list. So that's here we have our list argument in the end, right? So that's the list of A's that we are processing. And if we rename T2 to R, because that is our result type, R for result, okay? And now the two extra arguments, cons and nil, they get these types. Cons gets a more complicated type. Nil gets a very simple type. The type of nil is just a result. That is the result that we use in the empty list case. That is relatively easy to understand. Cons, the argument of this cons, the type of this cons argument is a function that takes the first element of the list, and that is an A at this point, and takes the result of the recursive call, and that is an R, that's a result, and combines these two things into a new result, which is also of type R. Okay. Now, if we did the job correctly, so if we did play our abstraction game correctly, not just do we end up with a type correct function, but we should also be able to re-express all three functions above now in terms of our function fun. Right? We should be able to do that. That's the other part of the exercise. One part of the exercise is abstracting from a common pattern, which is what we've now done, and then re-expressing the functions that we have abstracted from in terms of that pattern. Okay, so let's try this. I'm going to call this elem prime so that we can see the old and the new versions next to each other. So it should still have the same type signature. And we get this extra argument now, which is the y. Okay, so which we are going to pick up first. That is this is an extra argument. And then we have a function that operates on a list. The rest is a function that is operating on a list. And that should now be expressible as fun applied to two suitable arguments. Right? To two suitable arguments, because if we apply fun to two arguments, the cons and the nil argument, we also get a function that operates on a list and results in something. So now we just have to fill in the fun argument. Perhaps for some of you, this is going to be clearer if I actually pick up the list as well. So elem takes an element and a list, right? And fun expects three arguments, the cons argument, the nil argument, and then the list it operates over. But I can also do this using partial parameterization, because this list is only going to occur as the last argument of elem on the left-hand side and as the last argument of fun on the right-hand side. And so I can equally well say that elem applied to just one argument is a function from list of A to bool, and fun applied to two arguments is also going to be a function of a type, some list to some result type. So as long as I choose the result type to be Boolean, the types are compatible. Okay. So now I just have to look at what to fill in for the cons and for the nil case. And by having given this type signature here, GHC, or the Haskell language server, already tells me that in this hole I need to put in a bool. Right? But because the second hole is the nil argument, and that is exactly the result that I want to use for the empty list. And I can just read that off my definition up here. The result for the empty list is false. So that one is easy. Here, I now have to write a function of type A to bool, because A is the element type of my list, also in the case of elem, right? Bool is the result of the recursive call of elem on the tail of the list that I'm getting access to. And I have to say, if I know the first element is this and the result of the recursive call is that, then what is the result for the entire list? And the easiest way to do this is just to actually write a lambda term. So I get the first element from the list, which is called x up here, which I'm going to call x down here as well. And then I'm going to get the recursive, the result of the recursive call. So perhaps I'm going to call this rec, or let's just call it R for recursive. And now I have to produce a bool, right, based on these two things. And I can basically, again, read this off here. So that's the whole point, right? We have been abstracting from the patterns so that we can ultimately just read off what we have to fill in by identifying the pattern here correctly. So here, what do? We compare y with x. We have y, we have x, so we can write this in exactly the same way. Or, right, we make a recursive call. But now, rather than having to make the recursive call explicitly, we have the result of the recursive call already. Right? This is done by fun. Fun is making the recursive call and is giving us access to it by passing it to the cons argument. Here we are defining the cons argument. This R is becoming the result of the recursive call. So now we don't actually have to write it recursively. We can just write lambda x r arrow y equals x or r. Okay, and this type checks, and we can convince ourselves that it actually works. So let's see. All right, let's see that our elem prime function works as expected. If we look for 3 in the list of 1 up to 100, it says true. And if we look for 0 in the list of 1 up to 100, it says false. And it actually also works with infinite lists. If we look for something that is near the beginning, or even like something slightly larger, we will still get a result. If we look for something that is not in the infinite list, of course, it will go on, but it does not use space, as we have been previously discussing. So this is just happily running forever. So it does actually behave exactly in the same way as our original elem function. Okay, so it does is a instantiation of the pattern, and we can do the same for map. So how do we do this for map? For map, again, we have an extra argument, and then we have a function on a list. So again, like map f is equal to fun, and then we get 2 arguments to fill in. The second argument is always easier to fill in because the second argument is the result that we have to produce in the empty list case. In the case of map, this is the empty list. And indeed, our whole also says we have to produce a list of b's here, right? So let's put the empty list here. And then for the cons argument, all right, we have to produce a function that takes an a and a list of b's to a new list of b's. The list of b's is the result of calling map recursively on the tail of the list that we get immediately access to. So again, the easiest is to write this using a lambda term. So we get the x, that's the first element of the list. We get the r, that is map fxs. And we just have to combine these two things, so we can read that off from here again. So we do fx cons r. And then map prime of +2 from 1 to 10 is giving us this, or map prime of even of 1 to 10 is giving us this. And let's say map prime of ×2 of 1 dot dot, even with an infinite list, this still works because, I mean, our results are produced incrementally. It behaves exactly like the original map function. Okay. Final example here was and. So and is list of bool to a single bool. So here we don't have any extra arguments. We just immediately dispatch to fun. The second argument of fun must now be of type Boolean. And we can read that off here. The result for the empty list is true. And here, in the cons case, we have to write a function of type Boolean to Boolean to Boolean, because our list here in this situation, in the AND case, actually contains Boolean. So the element of the list is a Boolean. The result of the recursive call is also a Boolean. Again, the easiest, probably, if we want to be systematic, is to write a lambda term. We get the x, we get the result of the recursive call, that is the AND XS, and we combine them using AND. So we write x and r. But now we can observe that what we have here is actually lambda xr arrow x and r. This is literally the AND function. This is like we take two arguments and we use them as left and right argument to AND. So we could just use the AND operator directly without even putting any arguments, which gives us a really short and concise way to write AND. So here we can actually say we've really won something, right? Versus this version to our new version. In the other cases, we still had to write a perhaps slightly complicated lambda term, even though we won a few characters by not having to do the pattern match anymore. So the trade-off is slightly less obvious. Okay. Now this worked well, and I mean definitely we managed to capture the common pattern, and it's a useful pattern that arises a lot of times with functions on lists, right? So it captures what I call the standard design pattern on lists. And so it's perhaps not surprising that this exists and has a name. And the name that this pattern has is foldr. So if we hide foldr, we can rename the function fun to foldr. Okay. And indeed, if I look at the prelude version of foldr, you see that it has a more general type again, so it actually works not just for lists. But if we think of the T that is supposed to be foldable as a list, then it has exactly the same type as our foldr. So just that the type variables here, it uses B rather than R, but it otherwise has exactly the same type. A to B is the cons argument, the B here is the nil argument, and it takes a list of A to a B. And basically all functions that we have been writing so far can be written using foldr. Some functions more easily, other functions it's a little bit harder. And the question is, of course, should you or should you not, right? I mean, now that you know about foldr, the question is, should you use it? And when should you use it? And that is a little bit of a tricky question, right? I mean, often there are more specific functions to use than foldr, and then they are better, right? If what you're actually writing is AND, or what you're actually using is map, then you should, of course, use AND and map and not write them using foldr instead. But if you're implementing a function such as map or such as AND, then you may consider using foldr. The advantage of using foldr is that you signal to the experienced Haskell programmer that what you're using is literally the standard design pattern on lists. There's nothing special going on. It is just a standard procedure. You do a pattern match on lists. You have these two cases. You have a standard recursive call on the tail. There is nothing extra, nothing strange going on. And that is immediately made clear because you're invoking foldr, and that captures exactly this pattern, right? There are some other list functions where you may occasionally need to consider an extra case. Sometimes you need an extra case for the one element list, although not all that often. And they would be much more awkward to write in terms of foldr, so you probably wouldn't. And then it sort of kind of becomes more clear, the distinction, right? This function follows the standard design pattern very clearly, so we use foldr. This other function doesn't, so we don't, right? So that is one of the advantages. Of course, sometimes by writing something using foldr, it also actually becomes simpler. In the case of and, I think, is a good example where things work out really nicely. This function that we have to write in the combined case is really just an application of an already existing function. And in such cases, using foldr is extremely compelling, right? Because it really also saves work. In other cases, such as the map and the elem case, perhaps it's kind of neutral, I would say. It's we still have to write some lambda term, which we then have to understand, but the lambda term isn't terribly complicated. And if you know that you get the first element and the result of the recursive call, what's going on here is relatively easy to understand. So so that's still fine, I would say, right? So in this case, in elem and map case, I would say it doesn't matter very much. The win is limited, but there's also no harm. So I think whatever you personally prefer. And then there are functions where it is perhaps enlightening to see that they can be written as a foldr, where it's a good training for manipulating higher order functions in Haskell and understanding what's going on. And but I wouldn't do it because they become more complicated if written in this way. And an example of such a function would be take or drop. They perhaps occur in the exercises as such training. The problem with take and drop is that they have this additional integer argument, right? And this integer argument changes in the recursive calls. So the good thing of the extra argument that elem and map have is that it never changes in the recursive call. So it's basically a global parameter, and then it's just used. So map takes this extra f, but f never changes. So in the recursive call, we just call map f again. Elem takes an extra y, but y does not change. In the recursive call, we just call elem y again. But take takes an extra n, and this n changes in the recursive call. We call take with n minus 1. So that makes everything more complicated. Drop similarly. Other cases like this exist as well. So in such situations, as I said, it can still be enlightening to see that foldr can actually be used to express these functions. So it's possible, but it is much, much harder, and the result is getting more complicated, I would say, more complicated to understand than the original function defined using pattern matching. So while it is good to have the skill to be able to do it, well, that is certainly good training, right? To be confident enough with Haskell to be able to do it and to understand everything well enough to be able to do it. I would, in an actual code, I would always strive for clarity and use whatever is clearer. Okay, so that is enough for this video. In the next video, I'm going to do the same thing that we just did, this discovery of the foldr pattern, for the functions that we have been writing using strict accumulators or in general accumulators. And we're going to play the same game of like identifying common parts and introducing names for parameter names for things that change, and see what we end up with for these functions, because all the functions that are written using an accumulator are also following a common principle. Okay.